Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very much, Sriram. Good afternoon, everyone, and my thesis is titled Mathematical Analysis of Programs. So I would like to start, and it's traditional to start with a slide containing pictures. And these pictures are supposed to show you the kinds of programs that I'm interested in and the kinds of analysis that I'm interested in. The programs that I'm interested in, not surprisingly, are programs that come from software programs, hardware programs, and embedded systems. I'm also interested in other sources of programs. By programs, in this case, I mean computational processes. And these computational processes can come from many other domains, such as manufacturing systems and biological systems. Analysis is traditionally termed as the understanding of programs. And by understanding of programs, we wish to find bugs in programs, we wish to find unhandled exceptions, and we wish to find bad situations that we do not wish to occur in a program's execution. On the other hand, for a manufacturing system, we would like to find bounds on the throughputs of the manufacturing system, the absence of a deadlock in the manufacturing system. For biological systems, we would like to understand the biological system and find differences between the model and the actual experiments. So these are all instances of programs and program analysis problems. And I would like to talk about some of these programs and program analysis problems in my thesis. So let me start with a very trivial example of the kinds of programs that I'm interested in, the kinds of programs I handle, and the kinds of analysis I do. Here is a very trivial program. It just has two integers, I and j. It starts with I equals 2 and j equals 0. The program has a very simple loop, and there are two ways of going around the loop. In one way of going around the loop, you increment I by 4. The other way of going around the loop, you increment I by 2, and you increment j by 1. Now, if you stare at this program for a second, then I can immediately convince you that I greater than or equal to 2 and j greater than or equal to 0 are invariants. They hold on every single run of the program. And the reason being that I starts from 2 and can only increment over the program execution, similarly for j. What may not be so obvious is that I minus 2j greater than or equal to 2 is also an invariant. What I'm interested in is when you give me a program description of this sort, compute such invariants automatically. But this needs to be tempered down. The sorts of programs I'm interested in are programs that work on numerics, programs that handle numbers. I call them numerical programs. The sort of invariants I'm interested in are numerical invariants, invariants of the form I minus 2j greater than or equal to 0, and so on. So my thesis comes up with techniques for generating numerical invariants for numerical programs. What are the applications to work like this? One such application is buffer overflow analysis. Here's a simple C program. It has an array A of size n, and it has an array access at line 5, A of I and A of 2j plus 1. If we could prove the invariant, the numerical invariant, 0 less than or equal to I less than n, or the numerical invariant 0 less than or equal to 2j plus 1 less than n, then we have shown that this program, at least at point 5, is safe from buffer overflows. So buffer overflow analysis is a very important application of numerical invariant generation. Another interesting application is that of division by 0. So here's a program, and here's an expression A equals A plus B by C plus B minus 1. And if we could prove that C plus B minus 1 was greater than 2 or less than minus 1, or in general not 0 at that point, which is again a numerical invariant, then you have shown freedom from division by 0 bugs. So there are specific kinds of bugs like buffer overflows and division by 0 bugs, which depend on your ability to generate numerical invariants and reason with numbers. So to summarize, where do numbers come from in a situation like if you take a C program and you wish to come up with a numerical program? And C programs have many features in them which are not numerical: arrays, strings, pointers, heaps, system calls. And there are a bunch of features in any high-level language that's inherently not numerical. What I would assume throughout this talk is a process of abstraction by which you abstract arrays into information that you require, like array lengths. You can abstract the contents of arrays into summary dimensions. You can abstract strings by their lengths, by the position of the null terminator, and so on. You can abstract system calls by what they do on the numerical variables in your program. And I'll assume a sound process of abstraction by which you could take any high-level language program and come up with a numerical program, so that any inference you make on the numerical program, such as invariance, can be taken back to the C program, and you can deduce useful properties, such as buffer overflows. And I will assume this abstraction, and I'll talk about how to do the numerical part of the analysis, and then later talk about the details of the abstraction. The advantage of this abstraction, I claim, is that by doing a more sophisticated analysis on numerical programs, you could find more subtle bugs. There are other applications to this line of research. One such application is that of manufacturing systems. And I bring this up because manufacturing systems are very similar to computer networks. They involve widgets going around in assembly lines and being manufactured, going through different stages of manufacturing and coming out as a product. The difference between a manufacturing, so it has the same problems as computer networks. It has buffers. It suffers from resource contention. You need to reason about buffer lengths. You need to prove that widgets never get dropped, things get manufactured, and so on. But the main difference is that there is an economic reason for which manufacturing systems and the mechanisms underlying them have to be designed very carefully. If as a network designer you could invest $50 and get an extra 50 packets through a network, that's not very important. But if you could manufacture an extra 50 cars a day, that is extremely important. And there are whole departments with researchers in them who work on fields like this. One of the interesting problems in manufacturing systems is that you need to reason about the absence of deadlocks. And here's a model of a manufacturing system. It's called a Petronet model, and I took it from a robotics journal. I'll be talking about this later in my talk. But to prove models like this are deadlock-free is beyond the technology that we have right now. Things like model checking cannot work here. And numerical invariant generation is one of the tools that I use to handle models such as these. Other applications stem from systems biology. With a lot of data about DNAs and genetic sequences, people are now beginning to understand how fundamental processes of life work in terms of circuits and in terms of decision circuits. Here's one such process. It concerns a virus called phage lambda, which infects a bacteria. When it infects a bacteria, it has two decisions that it can make. It can either decide to kill the bacteria and replicate instantly, or it can decide to integrate with the bacteria and replicate when the bacteria itself replicates. The decision circuit for this is well known. It has been modeled, and models of the decision circuit take the form of something that is being studied by program analysts. It's called hybrid systems. And there are hybrid system models for biological systems such as this. Applying my program analysis techniques on models such as this, which primarily involve reasoning about numbers, gives me an interesting way of applying my techniques to a larger field such as biological systems. To summarize my motivations, I am motivated by traditional program analysis concerns, such as buffer overflow analysis, division by zero analysis, runtime safety, reachability, and deadlock freedom. These are all traditional program analysis techniques which will benefit immensely by good invariant generation. Some compiler optimization techniques, very few of them, like constant propagation, things which are used in compiler optimizations, can also be viewed as invariant generation. Invariant generation is also used in other so-called non-standard applications, and I list two of them: manufacturing systems and regulatory networks. So let me summarize my contributions. And before I do that, let me start by summarizing the state of the field approximately circa 2000 when I started my PhD. The world of numerical systems, programs that deal only with numbers, is divided into two parts: linear systems and nonlinear systems. In nonlinear systems, it is possible to multiply a variable with another variable. And in linear systems, every assignment and every decision of your program has to be a linear expression. There were algorithms for linear systems. You could use polyhedral analysis. You could use intervals and octagon analysis, something I'll be describing in detail. And there were a few more algorithms for systematically handling a linear system. But there was no known algorithm that could take a nonlinear system and systematically handle it. And this was the state of the field for numerical invariant generation circa 2000. So here's my contribution. I will show you a polynomial time polyhedral analysis using linear program that actually scales. Traditional polyhedral analysis does not scale because of the exponential space complexity of the polyhedral operations. I'll show you how that can be done in polynomial time if you are willing to make some sacrifices. I will also show you a completely new way of doing analysis, and this is called constraint-based analysis. It's not new from the viewpoint of program analysis, but it's new from the viewpoint of numerical program analysis. I will show you how to do it for linear systems using a theorem from linear programming known as Farkas Lemma, and I'll show a first systematic algorithm for nonlinear systems using something known as Groebner basis. So here's the outline of my talk. I shall describe my algorithm for polyhedral analysis. and then I shall summarize constraint-based analysis. And I shall end my talk by talking about some emerging trends and my plans for future research. Let me start with polyhedral analysis. And before I go into polyhedral analysis, let me make the definition of invariance that I loosely defined in my first slide into a formal definition. An invariant is simply defined as an assertion that's true in every reachable state of your program. So if an assertion holds at every reachable state of your program, it's an invariant. And the Venn diagram shows the reachable set of states, which is the blob in the middle, and the invariant states, which is the rectangle surrounding it. The key insight from this Venn diagram is that an invariant is an over-approximation of the reachable states of your program. And so any process that generates a guaranteed over-approximation of the reachable states of your program is an invariant generation process. Here is a simplified version of polyhedral analysis. And polyhedral analysis computes a guaranteed polyhedral over-approximation of the reachable states of your program. So it generates polyhedral invariance. So you start polyhedral analysis by taking a polyhedron that wraps around the initial states of your program. So if your program starts with I equals 0 and j equals 0, that's a polyhedron right there, and that represents the initial states of your program. I'll call this polyhedron reach 0, the set of all states reachable in 0 steps. Starting from this polyhedron, we could do a post-condition operation. Take each statement in your program and do a post-condition. This is a simplified presentation of the analysis anyway. So you do a post-condition, and you could now compute a polyhedron of all the states reachable in 0 or 1 steps. You could do a post-condition again, and you get 0, 1, or 2 steps. Theoretically, you could keep doing this infinitely often, and you may not converge to a polyhedron. But if you did, then that polyhedron is guaranteed to contain all your program behaviors and all your program states, and it's guaranteed to be an over-approximation. In practice, you force this technique to converge by an operation known as widening. And if you do widening repeatedly enough, you're guaranteed to end up with a polyhedron, from which if you start inside the polyhedron and execute any program state, you're guaranteed to stay inside the polyhedron. Then your procedure has converged. You have a polyhedral over approximation of the reachable states of your program, and that's how polyhedral analysis works. This analysis has been used. It's a very natural analysis for linear inequalities, and it's been used very widely in the domain of hybrid systems, especially the work of Hensinger in high tech is very. It uses polyhedral analysis in a very non-trivial way to infer really good invariance for hybrid systems, and it's very popular among control theorists. The problem with polyhedral analysis is that it's exponential space in the number of dimensions of the program. If your program has 50 variables, then it's potentially exponential space. And the way to see this is you take every polyhedron has 2 representations. You can represent a polyhedron by the sides of the polyhedron, or you can represent the polyhedron by its vertices. And if one of the representations is compact, the other representation could be exponentially larger than the first representation. So any operation, and the most frequent operation that's cited here is convex union, leads to an exponential space algorithm. The algorithm for convex union of 2 polyhedra is known to be exponential space. And so the algorithm uses polyhedral operations that are exponential space, and in practice it does not scale very well, and it's never been used on a scale of programs. So no one has taken a C program and done polyhedral analysis on it. And one of the simple reasons is that it simply does not scale. There are other solutions that do scale, and they have been used on practical programming languages. And these solutions fundamentally work like this. While polyhedral analysis says that you can use any shape of polyhedra as intermediate polyhedra in your analysis, these analyses, and I've shown you 2 of them, they are called intervals and octagons. These restrict the shape of the polyhedra that you can encounter in the middle of the analysis. So in interval analysis, the polyhedra are all restricted to be rectangles. In octagon analysis, the polyhedra are all restricted to be octagonal shapes. And if you look at it in the constraint terms, in interval analysis, you are restricted with constraints of the form L less than equal to xi less than equal to u, and these are rectangles. In octagon analysis, you are more or less restricted to difference constraints, xi minus xj for each pair of program variables less than equal to L. So these are the restrictions under which intervals and octagon analysis operate.
What's the citation, min 01?
Antoine Binet. The E doesn't. Sorry.
Very long last name, right?
Yes. So intervals and octagons work in polynomial time, and the reason they work in polynomial time should be pretty obvious for intervals. It's very easy to take the convex hull of two rectangles. You just take the minimum and take the maximum. That's easy. For octagons, there's a way of doing it using the shortest path algorithm. You could use Bellman-Ford, you could use Floyd-Warshall, and there's a way of making a shortest path algorithm work for octagon analysis. And so these are very specific to the kinds of constraints. If you said I wanted to look at an invariant like xi minus 2xj, that would break the octagon analysis algorithm as it is. So the natural question to ask is, what happens to pentagons and why not dodecahedra? And so here's my contribution. In my contribution, you could fix any left-hand side. So both intervals and octagons work because they fix the left-hand side. So my contribution is that you could fix the left-hand side, and all you have to do is just find the right-hand side. And that's what your analysis does. And that just makes it polynomial time. And that's the proof that any weakly, though these are called weakly relational domains, and any weakly relational domain, that is an analysis where you fix the left-hand side and you just want to find the constant coefficients, is polynomial time solvable.
I don't understand what that means. How do you mean fix the left-hand side? What does that mean?
This is what it means.
Okay, all right.
So assume that the user has given you. So I will ask you to make this assumption for this slide. Assume that the user has given you x minus x, y minus y, minus 2x plus y, and x minus 2y. The goal of your analysis is to find the C1s through C6 that makes this entire thing an invariant. And if you look at it, that's how octagon analysis worked. You assumed xi minus xj, and you found the b. So in this case, I ask you to assume more. The user gives me more things, and these aren't xi minus xj, but the user could have just given me octagon analysis. Right? So in that sense, it subsumes octagon analysis, subsumes interval analysis, and just takes what's important from them and what makes them polynomial time, which is the assumption that your left-hand side is fixed and your right-hand side, which is the constants, is something to be determined by the algorithm.
Could it happen that you might have to, one template is just not possible to find any C6, any C on the right-hand side, then you might have to drop it, something like that?
Yes, you could set it to minus infinity.
Oh,
okay. So the algorithm works by just considering instantiations. Instantiations could be real numbers, plus infinity, minus infinity. Each of them has a meaning. Minus infinity means you drop it, plus infinity means it's false. So you work on the extended reals. And this defines a family of polyhedra. So I've given the user the power to define a family of polyhedra, and my analysis is just restricted to use polyhedra that belong to this family and no other polyhedra. This immediately makes my algorithm tractable. But before I go into that, let me show you some techniques for actually forming this template. And where do these templates come from? One big source of the template is just the target property you wish to prove. You have a program with array accesses. Take each array access and say, if a of I is an array access, then I minus the allocated length of a is a template. This could be any expression inside. It could be a of 3j plus 2k plus 1. In that case, you just say 3j plus 2k plus 1 minus the allocated length of the array is less than equal to something. And that needs to be tracked. So if you have a target analyzer in mind, that gives you a set of templates you could start with. Now, once you have started with a set of templates, you could use techniques such as support assertions to enrich the set of templates to add new expressions. Here's one way of doing it. Here's a statement that goes from L1 to L2 and just assigns x to x plus 2y. If you need to prove that x is greater than or equal to something at L2, then you need to prove, or you might want to prove, that x plus 2y is greater than or equal to something at L1. So x plus 2y is a natural template to be added at L1. And what my technique supports, this is one additional advantage, is that it supports different sets of templates to be defined at different cut points in the program. And you could use a precondition. This is just an operation of taking a precondition to compute more templates that need to be tracked. And this works very well in practice. Another idea is to use something known as increasing expressions. Here's this program statement. It says x is x plus 1 and y is y plus 2. The template 2x minus y is very important because it's not changing. When you take 2x, when you prove 2x plus y greater than or equal to 5 on the left-hand side, then the proof just goes on to the right-hand side, all other things remaining equal. So you could use a constraint generation process. So the way I do it is I say, I say, let me take an expression of the form c1x prime plus c2y prime greater than or equal to c1x plus c2y. c1 and c2 are unknowns. X prime and y prime have expressions, linear expressions in terms of x and y. I could just substitute it solve for C1 and C2, take each solution and just put it as a template. So this is a simple idea that lets me get templates that I can use.
Shreyam, I have a question. We need to back up a few slides. There was a slide where you gave a table of complexities, right?
Yeah.
What exactly, precisely, is the problem for which you have given the complexity?
So the complexity is in the number of dimensions. So any abstract interpretation. So if you take any abstract interpretation, it should be. So any abstract interpretation algorithm works like this. You associate an abstract object with each location, each cut point in your program, and now you're going to solve the data flow equations by you're going to compute a fixed point iteration. So it's typically linear. You use a linear number of operations on the number of cut points, right? And the number of joins is restricted because you can always widen and just converge fast enough. So what these operations are they are on the dimensions, the number of variables that you're operating over, and that's important for. In fact, that's very important for every numerical program.
No, what I meant was, what is the problem in the sense that this is the complexity of this is the time or space it would take for the problem to terminate, the fixed point computation to terminate?
Because it's the complexity of the most costly abstract operation, abstract domain operation. In this case, it happens to be join.
This is the complexity. Oh, I see. So the join is taking the union of two polyhedra.
Yes.
That's what is an X ray. I see.
The convex hull. And that's
Okay. Now I understand. Go ahead.
You had a question? Okay, to summarize my algorithm, I work in two phases. And the first phase is I construct a template. The second phase, I perform the analysis. So I'm just dealing these two phases, and constructing the template is you start from the target property and do a pre-operation a few times, and it doesn't converge, but that's okay. And then you perform the analysis, which is just solving a fixed point iteration. And each domain operation has been well defined, and it can be done in polynomial time. And the idea is to reduce each domain operation to linear programming. And the details are in my paper, which appeared in VMCI this year. So you reduce each domain operation to just a linear programming problem, and you solve polynomially many linear programming problems to solve for each domain operation. And linear programming can be done in polynomial time if you use interior point techniques such as Karmarkar's algorithm, or if you use a Simplex algorithm, which performs very well in practice. And for all practical purposes, Simplex algorithm is just polynomial time as far as we are concerned. There are problems with floating points, but I've seen that you can round the floating points up and later verify that something is an invariant. Coming up with invariants is a much harder problem than verifying invariants. So I would rather use floating points, come up with invariants, and then verify them later on. And that seems to work fine. So I've never had any problems with floating point, even if I round things like 2.4999 to 2.5. So to summarize, the program analysis is just polynomial time in the program and the template constraint size. So this is very important because in some domains, the template constraint size itself is exponential. Finally, let me talk about the performance. I ran this program on benchmarks, which are just transition systems, linear transition systems. I obtained them from many sources. Some of them came from the high-tech benchmarks. Some of them came from other projects that work on similar problems like integer analysis. There's a tool called FAST, and they have a set of benchmarks. And I just took all their benchmarks and compiled them. I have benchmarks that range from 3 to 52 dimensions. And these benchmarks are typically constructed for polyhedral analysis. So they have a few problems on which polyhedral analysis will work and a couple of problems on which polyhedral analysis fails. So I've shown you the performance on two problems on which polyhedral analysis fails. And one of them is called Big Java. It's an abstraction. It's a numerical abstraction of the producer-consumer thread implementation in Java. And it's been done by hand as far as I can gather. The other one is a Petrinet. It's called Mesh 3x2. I automatically constructed a template in both cases. In one case, I started off with the target property and just went back and constructed the template. In another case, I said do an octagon analysis, but enrich the octagons by adding all these support assertions and increasing expressions. So my analysis converges very fast. And the key thing that I want you to take away from this is that I solve a large number of linear programs, around 100,000 and 200,000 in each case. And the size of each LP, by the size of a linear program, I mean the number of constraints plus the number of variables. And it's around thousands, in the order of thousands. Excuse me. even for the largest program. So the key thing to note is that linear programming technology can solve problems which are 10 times this size, 100 times this size if you are willing to invest in a commercial linear programming solver. And linear programmings have million variables plus constraints have been solved. So this compared to LP, the sizes of LPs that are being handled these days, this is nothing. And I can easily go 4 to 5 times and not even notice the difference. And all these examples, even these 2 examples I've shown here, are beyond the reach of full polyhedral analysis. I can give them a day and they won't terminate. And in both cases, I think I proved the target property, which I was supposed to prove. So it performs well, and there's a lot of scope for implementing this algorithm onto a full-fledged C program analyzer. So let me move on to the next topic, which is called constraint-based analysis.
I have a question. Right? So you got to figure out how many times you do join and when you start doing widening, right? That's the game. So how did you do that for these programs?
These programs, I just fix a number, 4 or 5. That's called the naive iteration. So
you do join for 5 iterations and then you start widening. If you, for example, well, how did you arrive at 5?
Let's see. I think 5 is the smallest number for which I gained an improvement on one of my programs.
Meaning gain an improvement over?
Most programs, it doesn't matter. Beyond 3 or 4, it doesn't matter whether you do 5 or 7. Right? So I just scaled it up until I could see an improvement, and 5 seemed
improvement meaning comparing your program to the polyhedra approach.
No, comparing my program with n equals 4 to n equals 5.
Oh, I see.
Comparing with polyhedra, on some examples I'm worse than polyhedra, on some examples I'm better than polyhedra. Because when we do widening, there's really no comparison. You cannot say that this algorithm is better than polyhedral algorithm.
What is confusing in the way you say it is actually in one case you're talking about scaling, in the other case you're talking about precision.
Right.
I think you should be careful about.
Yes.
When you say n equals 4, n equals 5, you're talking about precision, right?
Yes. N equals 4, n equals 5, you're talking about precision. It's not a scaling thing at all. And as far as precision goes, it's hard to say. I have some examples where I will do better than polyhedra. For some examples, I'll do worse than polyhedra. And there's no theorem that says that I'm worse than polyhedra guaranteed. But the only theorem I have is that I'm guaranteed to be better than octagons. I'm guaranteed to be better than intervals. Because you implement your favorite interval, in terms of precision, I'm guaranteed to be better than intervals. Because you implement your favorite interval analyzer, and I would just use the interval templates and enrich them with more templates. And I have to get better invariance than you do.
So these programs, were you able to prove the desired property for n is equal to 2, or there you got like a false counterexample? Do you remember?
No, for most programs, n equals 2 is too low. I don't think it works.
I see. Okay, but for n is equal to 5, you were able to prove the property. Okay.
So, what's the approximate number of templates you have to generate?
For the largest program, I had to generate around 1,000.
And is there a theorem that says you don't need exponential number of templates?
No.
So you could potentially have exponential.
Yes.
But still your algorithm is polynomial.
No, algorithm is polynomial in the size of the templates and the dimensions. So you can see that here. Actually, I have 1,240 templates and 44 dimensions, and the average size of the LP is 1,280. It's just add the template, and that's how it works.
Did you also use narrowing?
I'm sorry?
Did you also use narrowing?
No, I did not use narrowing. That's something I could use to improve the result. Yes.
Generate all the templates, or
In one case I did. In Big Java I did because it had a target property. For Mesh 3x2, I think I gave the target property and I asked it to do an octagon analysis and then improve upon an octagon analysis by adding templates to it.
how many pre-operators do you sort of reach?
I limit that to 2 because I do not want too many templates, because it's too many templates means that I don't get anything out of it, and there's a lot of redundancy in these. So you have x greater than equal to 2, and then you have x plus y greater than equal to 2, and you have y greater than equal to 0, and that there's a lot of redundancy here, and you have to get rid of the redundancy. And one thing I've done very recently, is I've worked on methods for compressing linear programs. So reducing the number of columns and reducing the number of rows. And it seems to be worth the effort, because to compress a linear program, you solve other linear programs. And it seems to be worth the effort in doing that, because then the process is much faster. And I think for this example, I've gotten down the size of an average LP to be 400, which is saying something, just by doing LP compression.
So is my understanding right that each template forms a sort of a side of a polyhedron?
Yes, it forms a half space.
Right, and so since there can be exponential number of such things, when the same thing is true in polyhedra too, right? You can have exponential number of faces. Why is your method better? I mean, why does it work better than polyhedra?
Because you have fixed the number of templates, right? So you say you have fixed the number of templates to 1,000. The 1,133 here is something that I generated beforehand and gave it to the analysis, and that never changes during the course of the analysis. So that's the key difference. In polyhedra, what happens is these schemes keep getting generated, and soon you end up with a large number of templates or half spaces. In this case, you just restrict yourself, and so you're okay.
So if you fix the polyhedra, you can only move the
Yes, you can only produce new polyhedra by moving, or you could drop sides, and that's another way of producing polyhedra. So I'll move on to constraint-based analysis. So far I've assumed that analysis is done by taking abstract objects and doing a fixed point iteration. In this line of work, I will try to get rid of the fixed point iteration. And here's how I'll get rid of the fixed point iteration. I will start with a target invariant property, a template. So in this case, if you're interested in doing linear inequality invariance, start with a template c1x1 plus c2x2 all the way up to cnxn plus d less than equal to 0. And the key idea is cn through cn and d are unknowns. These are parameters for which I need to find values. What I do is I generate constraints on c1 through cn and d that guarantee that the whole thing is going to be an invariant. I solve these constraints, I just plug in the solutions, and I'm done. So this is very easily described, but the key thing is to go from the key conceptual step is to do step 2, and the key computational step is to do step 3. So generating the constraints is where all the concepts come in, and solving them is the hard problem in terms of computational efficiency. So let me show you how to do this. And before I go on to it, I'll briefly define the concept of an inductive invariant. So far we have just looked at invariants, but they were inductive invariants in disguise. So an inductive invariant is defined as an assertion that holds at the starting state of the program. So phi holds when the program starts. And for each statement, if phi held before the statement, then phi holds after the statement. It's a standard definition from high school literature. So phi holds at the start state, and phi keeps holding on every single trace, so phi holds everywhere. So that's the key behind an inductive invariant. So let me go back to my example in the first slide. So I have abstracted away everything and just left you the essence of the example. So there are 2 integer variables, and there are 2 paths, and this is the example from my first slide. Let me assume a target invariant c1i plus c2j plus d less than equal to 0. If I assume the target invariant, I am after c1, c2, and d that make it an invariant. So let me first encode initiation. Initiation is encoded as I equals 2 and j equals 0 implies c1i plus c2j plus d less than equal to 0. So this is the implication that needs to be encoded. And my question is, what are the constraints on c1 and c2 and d that guarantee that this implication always holds? And in this case, you can simply substitute I equals 2 here in c1i and j equals 0 in c2j. And the constraint you get out of it is 2c1 plus d less than equal to 0. The 2 because I equals 2 is a constraint. But this seems like a sleight of hand. So is there a general technique by which I can encode an implication such as this? And the key to the implication is there is a system of linear inequalities on the left-hand side, and there's a single linear half space on the right-hand side. So how can I encode implications like this? And the answer comes from a very well-known theorem that people have known for 100 years now. It's called Farkas Lemma. And Farkas Lemma works like this. You have a system S of a conjunction of linear inequalities on the left-hand side, and you have a single linear inequality on the right-hand side. And you ask the question, under what conditions on all the coefficients a11 through am and b1 through bm, c1 through cn and d, under what conditions on these coefficients does S imply psi? That's the key insight behind Farkas Lemma. And the conditions are that there exist real multipliers and some constraints on C1 through Cn and D whole. But I mean, just ignoring what the actual statement of the theorem is that it gives me a systematic way of encoding the initiation. So initiation is just the implication I equals 2 and j equals 0 implies something. This fits right into Farkas Lemma. I could do Farkas Lemma, get the constraints, do an elimination. It's an existential quantifier elimination, and I get a constraint. So it's not a sleight of hand, and it can be automated, and that's the key point behind presenting Farkas Lemma. So I could do consecution too, and consecution works on the same idea. Take each statement of your program. If phi holds before the statement, then phi holds after the statement. In this case, I have C1i plus C2j plus d less than equal to 0. I take a program statement, and I need to prove C1i prime plus C2j prime plus d less than equal to 0. I could use the same Farkas Lemma to do this, and I get the constraint 2C1 plus C2 less than equal to 0. I will not go into the details of the constraint, but this is what I end up in this case. I could do it for the other transition too, and once I'm done with all that, here's the summary. So I've fixed the target template assertion with unknown coefficients. I compute constraints on the unknown coefficients, and I get constraints in this case 2C1 plus d less than equal to 0, and so on. I get these constraints that I've shown here. I solve these constraints. In this case, there are two solutions, 0, minus 1, 0, and minus 1, 2, 2. Every other solution is just a combination of these two. And if I plug in these solutions, I just get the invariants I require, j greater than equal to 0, and I minus 2j greater than equal to 2. And these describe the state space of the program exactly. If you're wondering about I greater than equal to 2, it's just a consequence of these two invariants.
But are you guaranteed to generate all the
I'm guaranteed to
linear
generate
facts
all the
this
linear
way?
inequality invariants this way. Yes, but that means that I do an exact job of constraint solving, and that works only for systems with less than 5 variables.
Is this the first analysis ever to compute the exact set of linear inequalities for these kind of programs?
Yes, but you need to be very careful when you say compute all the linear inequality invariants. It means that I'm computing all the linear inequality invariants that are inductive just by themselves. Right? Take a program where you start with x equals 1, and every step you are just flipping the sign of x, so 1 and minus 1. If you want to prove x greater than equal to 1, that's not inductive. Or x greater than equal to minus 1 is not inductive. X less than equal to 1 is not inductive, but the conjunction of the two is inductive. So you could have case where A is not inductive, B is not inductive, but A and B is inductive.
Oh.
But this technique will just extend to that. Just parameterize it to C1i plus C2j plus D less than equal to 0 and D1i plus D2j plus E less than equal to 0, and you'll get that too. So it's, it is the first known complete algorithm, but there are two pinches of salt. One is that completeness is overrated, because there are programs where you have to prove x equals y squared before you can prove that, before you can prove an inequality invariant, you have to prove a nonlinear invariant. That's well known. It's not complete in itself. And then you need to do exact constraint solving, and that's a problem. You cannot do exact constraint solving, because one of the things that I very neatly hid under the carpet is that the constraints you get can be nonlinear sometimes. In this case, it wasn't. In some cases, it can be.
But that program in which you were flipping one, right? You could deal with that here, right? Because
I could deal with that here.
conjunction of linear inequalities there.
Yes, but it's a conjunction of two linear inequalities, and
You're generating conjunctions here, aren't you? Because you generated.
But each of these is just a linear inequality invariant by itself. J greater than equal to 0 is
Oh, I see. Okay.
But I could do that, and you need to just change the problem a bit. So you change your target invariant to a conjunction of two target invariants, and
But does Farkas Lemma work with that?
yeah, you just so if you have A implies B and C, that's just A implies B and A implies C. So just decompose it, and Farkas Lemma will work. What Farkas Lemma will not work is for disjunctions.
I see.
In fact, it works for any convex problem. If you can prove that the left-hand side is convex, the right-hand side is convex, you can apply Farkas Lemma.
So when you say target invariant, it's really target inductive invariant.
It's a target inductive invariant. But every known technique for generating invariants is a technique for generating inductive invariants. There's no such technique as something that generates just invariants. You always generate inductive invariants.
Yes.
Because you have to prove, you need a proof, and I can't trust your thing to be the correct thing.
Say again, if you have two constraints on the right-hand side, how do you make sure the coefficients come out different for the two constraints?
You just give them different, set them different parameters. So C1i plus C2j plus d less than or equal to 0, and then you say D1i plus D2j plus E less than or equal to 0.
But then if you have a solution for one of them, then you could find the solution. Just take the same values for the other, right?
Yes, but what you could do is you could always say that they are not equal.
Oh, I see.
That's a solution, or just get all the solutions, and among the solutions you'll have those solutions where they're equal, and you'll also have solutions where they're not equal. But so far I've just worked with k equals 1. K is the number of conjuncts I fix, and that seems to be good enough. I reported this in a SAS paper a year back, and I have a table where I list my technique and polyhedral analysis on the same problem, and I compare the invariants, I compare the times, I compare the invariants, and I show that there are cases where this technique works, where I can finish the constraint solving and get the invariants, whereas polyhedral analysis will not. And there are cases where it does, in most cases it does much better than polyhedral analysis. Even though polyhedral analysis can in theory discover conjunctions of 2 invariants or 3 invariants, I just discover single linear inductive invariants, and I get invariants that are beyond polyhedral analysis. So this is a very powerful technique for doing it. It's extremely powerful if you can do a good job of solving the constraints, but you don't have to. You can do a weak job of solving the constraints. Just look at the constraints on C1 through D and just get a few sample points from inside the constraints, and you have a few invariants. And even that is good enough. So here's sort of the largest canonical example that I solved using this technique, and it's a robotic system. It's a robotic assembly line system that I took from a robotics journal. It appeared in 1992. The reason why this Petri net cannot be solved using model checking is that it's not bounded. You can have as many tokens as you want in X1. That's a parameter you fix. So it's a parametric Petri net, and it cannot be solved using model checking because it's not finite state. If you fix the number of parameters, the colored place is the parametric place. So if you could fix that to 9, then spin would just grind through this in a few seconds and find me if there's a deadlock in this Petri net or not. But since I cannot fix it, I do not know. And the question that was asked here was, what is the limit on the number of parameters so that I could still operate this Petri net without having a deadlock? So that was the question that was asked, and it's an infinite state.
But I would guess that people solve this using Karp-Muller, coverability kinds of things.
No.
Using integer constraints.
Yes, some people have solved it using Pressburg arithmetic. So they actually managed to get the exact reachability set of this Petri net using Pressburg arithmetic. So in theory that proves, so people proved by hand that the answer is 9. So that's what the designers of the system did. They proved that it was 9 just by hand, and it's an entire paper. But then some people managed to find the exact reachable state space using Pressburg arithmetic. It took them 2.5 hours to find it, and I don't think they ever managed to prove it. I mean, theoretically, that huge assertion there should be able to prove that p less than or equal to 9, but I don't think they managed to. So what we did was we assumed that all these places can have real number of tokens. So we used a rational analysis, but we are still able to prove it. So it's sort of a compromise between doing exact integer analysis like reachability and coverability tree, and doing polyhedral analysis, which doesn't converge on this problem in any given amount of time. So the results, we modeled it, and there are 26 dimensions to the system. We discovered 2,000 invariants in 2 minutes, and we had a huge problem in filtering out the invariants that mattered and the invariants that did not matter. Some of the invariants were structural invariants, so-called traps of the Petri net. So Petri nets have many structural invariants that go like this. There is always a token between x1, x3, x7, and x9. That's some graph theoretic invariant. You could look at the Petri net, treat it as a graph, and you could just get all those invariants out. So what we did was we did just that, and we looked at all the structural invariants that we obtained by other techniques, structural invariants we obtained by our technique, and we took away the structural invariants, and there were still some invariants left over. So we used those invariants to prove deadlock freedom. And they did prove deadlock freedom, and they proved that the answer, which is if there are less than 9 processes in the queue, then the petri net is not deadlocked. So
how did you prove that last part?
we just proved it just by generating every deadlock situation and proving that our invariants preclude the deadlock situation for p less than 9. So just generate every deadlock on your concrete system and prove that that deadlock cannot happen if p is less than 9.
How did you know how to generate every deadlock?
It's easy in a petri net. You just say that some transition is disabled. So you go through each transition and say that transition is disabled. You cannot take the transition. So here's a transition. x23 goes to x25. I've omitted the numbers on this. So you could say that there is no token in x23, and there is no token in x21, there is no token in x22. So you can detail every deadlock situation just by going through the description of the petri net. Because a deadlock means that you cannot make any progress, and cannot make any progress is something you can just read off from the petri net.
It's not immediately obvious to me that there's a finite number of such deadlock situations.
Yes, in any system there is, because a deadlock just means that each transition in your program is disabled, right? So,
okay.
So it's just a state, a predicate from which every transition when you take leads to false. So you could do that.
Okay.
So it's a huge disjunct. In this case, it's around 600 disjuncts or so, but it's still possible to do it and take every disjunct and show that the disjunct is precluded for p less than 9.
So there's one disjunct per transition in the system.
Yes, something like no. One disjunct says one way of disabling each transition. So let's see. One way of disabling this transition, where I put the hand. I hope the hand is visible. One way of disabling this transition here is that x1 has no tokens. Right? One way of disabling this transition is that x1 has no tokens. One way of disabling this transition is that x5 has no tokens. So for every transition, choose one way of disabling the transition. Take the conjunction. That gives you one disjunct. Do it for every combination of every way of disabling. So it's a huge formula, but it can be generated, and every single disjunct is polyhedral. You can test it. And one of the cool things we did was we actually reverse engineered the model. We did not understand the model before. The description wasn't too good. But once we had our invariants, we actually show how we reverse engineered our models. And we have a paper in Zohar Manna's FESCRIFT in 2004, which shows how exactly we did this process, how we generated invariants, and how we solved this example. Now let me move on to nonlinear analysis. So far I have concentrated only on linear analysis, which means linear systems with linear invariants. Now I'll show you a systematic way of doing nonlinear analysis. And this is very similar to linear analysis. And all I'm going to do here is I'm going to switch in Farkas Lemma with something different, that's all. So in this case, I can take a nonlinear template, c1 x squared, x1 squared, x2, and I have shown you a nonlinear template there. And in this case, I'm going to generate equality invariants. Inequality for nonlinear invariants is too hard, and I haven't handled it. I'm going to generate constraints on C1 through Cm and D, and I'm going to solve them, and every solution is guaranteed to be an invariant, excuse me. And the key is to switch Farkas Lemma with something else. And the something else here is known as Groebner basis and the theory of ideals. So these are computational techniques from algebraic geometry, and they're not very scalable computational techniques, but they will do the trick. And they will encode exactly what needs to be encoded. Implications of the form A implies B can be translated into a constraint solving problem. And here's a simple example just to show you how things like these are useful. So this is an exercise in Floyd-Hoare, in using the Floyd-Hoare inductive invariance method to proving a GCD or LCM. And it's a very textbookish example. So you have a program that simultaneously computes the GCD and LCM, and you wish to prove that it does. But unfortunately, unless you prove this invariant here, y1, y3 plus y2, y4 is x1, x2, it's hard to prove this using the Floyd-Hoare technique. You need a lot of facts about GCD, LCM, and you also need this fact. You can encode this invariant, and in this case, I've just shown you the relevant terms here. But what I would normally do is I would assume some degree d. You give me a degree 2, and I will generate all possible terms of degree 2, and I will just make up a template like that. And in this case, the constraints are simple linear equality constraints. The constraint solving problems for some reason is actually easier than the constraint solving problem for linear inequalities. And once I solve the constraints, I just get an invariant, I plug it in, and I'm done. So it's pretty much the same technique, except that Farkas Lemma is switched in and out for a different lemma which holds here. And it's actually very similar. I applied this technique to hybrid systems, and I applied this to nonlinear hybrid systems, something that hasn't been done before. And here's an idea. I took this problem from a physics textbook, and this problem concerns a particle moving in a magnetic field. So on the left, you have a reflecting barrier. So you have a reflecting barrier. You have a particle that moves from the reflecting barrier, enters a magnetic field, and since the particle is charged, a magnetic field will curve it around in a circle, and it comes back and bounces again on the barrier and goes into the magnetic field. So this is a very simple physical system, that the sort of systems that are studied under hybrid systems. And the key thing about the system is that the differential equations that describe the magnetic field are nonlinear differential equations. And A here is a parameter. And the problem asks you, for what values of A does the particle bounce in the same spot again and again and again? So that's a very typical problem from a physics textbook, and I actually took it from one. So you could solve it, and you could apply pretty much the same techniques that I described for discrete programs with a few modifications, and you get an invariant, and the invariant actually solves the problem. So this is very interesting because A, it does not need an explicit solution to the differential equation, because there are no explicit solutions to nonlinear differential equations. And B, it's the first known systematic technique for handling nonlinear hybrid systems and generating invariants for them. The key motivation for studying constraint-based analysis is, first and foremost, it's a different approach to the problem. People have tried doing abstract interpretation the standard way, where you do a fixed point iteration, for a long time. And the question of whether there is a different approach to the problem is itself very exciting. What this technique provides me is that I can leverage the power of constraint solvers. I've tried many constraint solvers. I've used convex optimization techniques. I've used sum of squares programming. I've used matrix pencils. I've used CLP style solvers. I've used QPCAD. And there's a lot of fields I can borrow on and take constraint solvers and just try out my constraints on those constraint solvers. And as constraint solving technology advances, I can do bigger and bigger problems. And that's the key idea. It's just finding the right constraint solver for your problem. And it's as simple as that. It's applicable in many domains. At least right now, it's applicable in more numerical domains than the other technique, than the abstract interpretation-based technique. For algebraic systems, I use Groebner basis. And I'm looking at techniques for doing nonlinear inequalities.
Actually, the constraint solver you used is the same, because the constraints on the C1, C2s are all linear constraints, right? It doesn't matter whether the actual system when the study is linear or non-linear.
No, the constraints are nonlinear constraints. I didn't show you cases where you could get nonlinear constraints, but I can show it to you later if you're...
But they arise only in the non-linear system or in the linear system?
In both cases.
The constraints that could arise could be non-linear?
Mm-hmm. But it turns out that in the nonlinear case, the constraints are easier than in the linear case. In nonlinear case, they become something known as, they are just eigenvalue problems. In linear case, they are something different, and I can discuss the constraints.
I guess that's hidden sort of in the math on the slide
on the
Farkas Lemma.
Yes.
I see.
And that's, so most of my research has just, a large portion of my research for the last 2 years has been just finding the right constraint solver and building the right constraint solver. And I managed to build one that scales. I mean, my first constraint solver was just take a quantify elimination algorithm for nonlinear, for the theory of reals. And that worked for very, very small systems, 3, 4, 5 variables. And I stopped at 5 variables because I couldn't handle more than that. But then I built CLP style constraint solvers based on very simple ideas from techniques like QCLPR and so on. So that scales to around 20, 25 dimensions. That's how I solved the Petri net example. So that's pretty much it. I've been building constraint solvers, taking other interval arithmetic is another idea. So I've been using other people's constraint solvers.
So hang on, so building a non-linear constraint solver, the stuff that you just did, right? You did not talk about exactly how you built that constraint solver in this talk, did you?
No, yes, I have it in my paper, but I haven't shown it here. And
I see.
So
you did that using known techniques, or you invented some stick?
I just did that using known techniques.
I see.
My constraints have a very specific structure, and I could go into the structure, but
okay.
Yeah, but yeah. So I have techniques which can handle that structure and which can It's just known techniques. Just keep the linear part of your constraints and rewrite the non-linear part until they linearize. And so it's just known standard CLP style techniques. There are interval arithmetic solvers too that just work right out of the box. So this comes with, there are many related approaches that use a very similar idea for doing invariant generation. There's a whole theory of Petri nets. There's something called P invariants that are solved in a very similar way, just by parameterizing for the coefficients. But they are equality invariants. There's a whole line of research on set constraints in program analysis, translating simple program analysis into constraint systems so that you can solve them. But set constraints work in a different principle. The main technique for solving set constraints is just iteration. So one could argue that it's just writing the data flow constraints explicitly and just solving them. But this is something beyond writing explicit data flow constraints. The constraints are data flow constraints, but I do not solve them by an iterative technique.
What is the relationship between set constraints and linear and non-linear analysis?
Set constraints. So the idea behind a set constraint is to say that the result of your analysis is an unknown set. So if you're doing reaching definitions analysis, then the set of all reaching definitions is an unknown set. Call it X. And then it comes up with all the constraints that X must satisfy to be a solution to the analysis. So thus far, set constraints are the same. It's the same philosophy as what I do. Say the result of my analysis is unknown template, and what are all the constraints that the unknown template has to satisfy. But then the solution techniques are completely different. So it's the same idea. So you could call it set constraints for numerical analysis. There's some work on symbolic bonds analysis of pointer arithmetic. It's a PLDI 2000 paper by Rugina and Renard that's surprisingly similar, but they use a very ad hoc way of handling inequalities. So when they have a parameterized inequality problem like A implies B, they use a very ad hoc technique. I would recommend you consult. If you're interested, you should consult this PLDI 2000 paper. It's very interesting because there are ideas from there which we could handle in a less ad hoc way just by using my techniques. This technique has been used in generating ranking functions for proving termination. In control theory, it's been used in generating Lyapunov functions for proving stability. It's been used in the control theory literature again to generate barrier sets, something known as barrier sets for reachability analysis. So let me finally conclude my talk by talking about the abstraction process, which I asked you to assume. So far I've built analyzers, and all these analyzers work on numerical programs. And most of my numerical programs are just benchmarks from other systems that solve numerical programs, or a very few C programs, very small C programs that I hand translated into a numerical program, just to find out for myself whether the translation works, whether the abstraction works. But what are the complexities involved in the abstraction process? And one of the key problems in the abstraction process is when you're handling things like pointers and arrays, you have to be very careful about the alias context. So alias analysis is a big problem in making this abstraction work, and we have built flow-sensitive, context-sensitive alias analysis tools, and they do not scale, and the scalability of those tools will restrict the scalability of my analysis. So there's really very little use for handling numerical programs very efficiently if the abstraction process itself does not work very well. So looking into flow-sensitive and context-sensitive pointer analysis, there's some work done by Wilson and Lamb, PLDI 96, and some very recent work on flow-sensitive and context-sensitive pointer analysis. And any such analysis can be used to make this abstraction process more efficient and generate more efficient numerical programs. So these days I'm working on evaluating and implementing my techniques on C programs. So I've written features in SIL, placeholders for pointer analysis, and just trying to build a buffer overflow analyzer using my abstract domain. So I should be able to use my abstract domain library once I get the other problems solved. I've also done other research, and I've done research on the analysis of publish-subscribe systems, where I look at publish-subscribe systems and come up with expressive languages for expressing event correlation in publish-subscribe systems. I've also worked on runtime verification. As a joint work with Synopsys, I designed a language for specifying and verifying runtime traces of hardware circuits. So we were given large traces of practical hardware circuits, and we we came up with a language by which we could specify the protocols like PCI and check compliance of the traces to the PCI specification. So efficient ways of writing specification and verifying specification. The key problem in runtime verification is to do this process online, where the circuit is running and my monitor is running concurrently with the circuit. So doing runtime verification that's as fast as a running circuit is a key challenge, and it's very hard to address, and it's an open problem. Finally, I'd like to thank you. Most of this research is done in collaboration with my advisors, Sohar Manna and Henny Sipma. I have implemented almost all my techniques, and everything is implemented, and everything is available from my webpage. And I urge you to try it out. And thank you very much for listening to my talk.